this question was about finding inverses for polynomials with integer mod n coefficients. So the first one, where's my piece of chalk? The first one was about finding an inverse for 2 plus 3x in polynomials with coefficients in Z9. So this is a little bit more exciting than just polynomials with integer coefficients, but still the principle is that what we want to look for is some a plus bx such that when you multiply it together you get 1 in this particular ring. Now, how do I know that this polynomial is only going to have degree 1? Well, I kind of don't, but I might as well look for one that's only got degree 1 first, and then if I find one, then I know I'm done. If I didn't find one, then I would have to go, is it going to be higher? Of higher degree. But let's just try and see if we can find one of degree 1. So if we multiply this out, we get 2a plus 3a plus 2b, 3a plus 2b, x plus 3bx squared equals 1. And now we can just compare coefficients, right? So by comparing constants, what we get is that 2a has to be congruent to 1 mod 9. Remember, we're comparing coefficients in the integers mod 9, so everything's happening mod 9. So how can we get 2a's congruent to 1 mod 9? Well, we could do some complicated way of solving this, but it's easier with these small numbers to just feel your way through a little bit. So one way you can work this out is you can say, oh, well, 1 is the same as minus 8. So what we're looking for is minus 4, which is the same as 5. Another way you can do it is you can just try a few numbers. You can say, how could we get 2a to be congruent to 1? Well, what numbers are there to congruent to 1 mod 9? 10. Oh, 10 is certainly congruent to 1 mod 9. And half of 10 is 5. So we can try 5. We can try a congruent to 5, which will certainly make this true. So then let's see if we can make the rest of it true. So comparing coefficients of x, we get that 3 times a is 5, 3 times a plus 2b needs to be congruent to the coefficient of x on this side, which is 0. So we need this to be true, congruent mod 9. And what that tells us is, well, 3 times 5 is 15, that's the same as 6. Right, so what we get is 6 plus 2b is congruent to 0, which is the same as saying that 2b is congruent to minus 6. So we could try b is congruent to minus 3, i.e. 6. So now we have a conjecture. We don't know that this is true yet, so we better jolly well check that it's true. We have a conjecture that, let me just write it over here somewhere, does 5 plus 6x work? Well, the last thing we have to do is check that 3b, so for the coefficients of x squared, we need 3b is congruent to 0. Now, 3b is 3 times 6, which is 18. Phew, that's congruent to 0. But we can do an even better check. We can just plug it all back in there and see if it's true, right? Because one thing we could do is just multiply it all out. I've just realised that this is a bit silly, because multiplying it all out is what we just did there. But if you really wanted to convince yourself, you could multiply out that bracket and show that what you got was really the thing you wanted. So what we get here is 10 plus 15x plus 12x, 15 plus, is that right? 15 plus 12 is 27. Did you notice me getting nervous there that I was going to do it wrong? And then you get plus 18x squared. But this is congruent to 0, and this is congruent to 0, and that's congruent to 1. So we do indeed get 1, which shows that this is the inverse of that, because they multiply together to give 1. Okay, let's do the second one and see if we can understand the second one. The second one was in integers mod 16, even more exciting. Excitinger and excitinger. Okay, so what we've got here is 3 plus 4x, and so we're looking for 3 plus 4x times a plus bx, and we want that to be equal to 0. So again, we multiply it out, and we get 3a plus 4a plus 3b x, and and then the x squared term is 4b x squared, and we need that to be equal to 1 in Z16x. So if we start by comparing the constants, we get 3a is congruent to 1 mod 16. Now, this is a little bit more exciting. We have to fiddle around a bit harder to try and find something that's congruent to 1 mod 16. So we're looking for something that's congruent to 1 mod 16 and divisible by 3. So if we just try it a little bit, well, 16 isn't going to work, because what's congruent to 1 mod 16? 17. That's not very divisible by 3. So let's try 2 times 16, which is 32. What's congruent to 1 if you take off 32? Oh, 33. That's divisible by 3. Good. So we could try a is congruent to 11. Now, of course, if your trial and error didn't work, you could solve this using one of those methods that you did in PMA 110. But if trial and error works, then fine. So try that, so that 3a is 33, which is certainly congruent to 1 mod 16. So the next thing we need from the coefficients of x is that 4a, which is 44, plus 3b is congruent to the coefficient of x over here, which is 0. Now 44 is congruent to 12 mod 16. So what we've got here is 12 plus 3b is congruent to 0, which means that 3b is congruent to minus 12. So we can just try b congruent to minus 4. Minus 4 is, of course, the same as 12. So now we have a conjecture, which again I'll put over here. So does a plus bx work? So a is 11 plus 12x. Does that work? 11 plus 12x work. Well, the thing we have to check is the coefficient of x squared. The coefficient of x squared is 4b, and that has to be equal to the coefficient of x squared on this side, which is 0. So we need 4b to be congruent to 0. But what's b here? b is 12. 4 times 12 is 48, and that's the same as 3 times 16. So 48 is divisible by 16, which means that 4b is indeed congruent to 0. So that's correct. And we can check by multiplying out the entire thing that 3 plus 4x multiplied by 11 plus 12x is, well, we get 33 plus, now cross terms, 44 plus 36. 44 plus 36, that's 80 x, plus 12 times 4 is 48, 48x squared, right? We know that 48 is divisible by 16, 80 is divisible by 16, it's 16 times 5, so we're left with 33, which we know is congruent to 1 in Z16x. So it's a good idea to multiply whatever you got back out again, just to give yourself another way of checking that what you did was right. And note that you could have written this as 11 minus 4x, that would also have done, or indeed minus 5 minus 4x, because the 12 is the same as minus 4 in this ring. So there are other ways you could do this, but as long as you multiplied them out and you got 1 again, then you know that this is the inverse of that, which is what we need to show. So that's the end of that question.